Welcome everybody. My name is Claudio Tesone. I am professor of blockchain and distributed ledger technologies. I am also the chairman of the Blockchain Center at the University of Zurich, and it is for me a pleasure to welcome you all to this event that is the first one that we are having here in the virtual pavilion of the World Expo in Switzerland. The reason on why we are here is because of activities that we have here at the University of Zurich, but also resorting on our international network of collaborations that led us to have this very high-profile event here in the metaverse. The University of Zurich is the largest in Switzerland, and we have the broadest range of activities and areas that are taught in our space in Switzerland. And one of them is blockchain and all the technologies that can be built around it. Because of collaborations with other units of the University of Zurich, but also with the Swiss Pavilion in the World Expo 2025 in Osaka, we started to design an immersive experience that you can now all enjoy inside of the virtual expo. And the aula in which we are now is a digital twin of the aula of the University of Zurich. This is a very historic element of our architecture, because in this aula that was built in the first half of the 20th century, right after the Second World War, Winston Churchill gave a speech calling for Europe to rise again after the devastation of the Second World War. And now we have the most prestigious talks, and we receive our most prestigious visitors inside of this aula, and this is why welcoming our speaker today is so nice in this regard. This would have not been possible without the trust that the President Switzerland had on us to have this presentation, but also because of the collaboration that we have with Metapiece that in a second will be introduced. This is just the first series of a very high-profile set of talks that we will be having in this virtual space. So if you're interested in this and in other presentations also of other Nobel laureates, we would be really happy to welcome you. And this is the schedule of the talks that we will have. As we say, it is for this series of Nobel talks is only possible thanks to the collaboration that we have with Metapiece. And this is, for me, a pleasure to welcome Yanis from Metapiece, who will introduce the role of the association and which are the activities that they are having now. Yanis?
So my name is Yanis Hegwein. I'm the president of the Metapiece Foundation. And it's wonderful to welcome you to the opening of Nobel Talks, Designing Progress Together. This series of virtual lectures held for the first time in the metaverse brings together the most brilliant minds of our time. It's a celebration of knowledge and shared responsibility for shaping our future. Science and technology are not only engines for innovation, but also pillars of peace and transformative development. In the spirit of this expo, Designing Future Society for Our Lives, Nobel Talks offers a platform for global dialogue, where Nobel laureates meet audiences from all walks of life across geographies and disciplines. The realization of this project is possible thanks to our dedicated partners. I extend my deepest gratitude to Professor Claudio Tesone and his team of the University of Zurich Blockchain Center, present in Switzerland, and all our supporters who have made this event a reality. Your dedication empowers us to build a space that is open and accessible, where young people and experts alike can explore the ideas that define us. Today, we are truly honored by the presence of Nobel laureate Takaaki Kajita, whose discoveries have fundamentally changed our understanding of the universe. Professor Kajita has generously agreed to share his wisdom with us, opening the journey of Nobel Talks. From the bottom of our hearts, Professor Kajita, we thank you for your insights, which set a powerful tone for the months to come. Please enjoy the talk ahead, and back to you, Claudio.
Thank you very much, Yanis, for your kind words. I will. I would like to once again mirroring the words by Yanis, to whom it's a very great pleasure to collaborate. It is for me a very great honor today to welcome our first distinguished guest in the session of Nobel Talks, Professor Takaaki Kajita, or how he would be respectfully addressed in Japan, Kajita Sensei, who received the Nobel Prize for Physics in 2015. Professor Kajita have become very internationally renowned for his groundbreaking discovery of neutrino oscillations, which revealed that actually they have a mass and completely reshaped our understanding of fundamental particle physics. He comes actually from a very remarkable scientific lineage because he completed his doctoral studies under the guidance of another Nobel Prize laureate, Masatoshi Koshiba, who won the Nobel Prize in 2002. This talk today does not only reflect the extraordinary contributions that Professor Kajita had to science during all his academic career, but also the legacy of discovery passed from teacher to student, which is actually something that is very rooted in the Japanese academic culture. I only want to say a very few things, and just as a humbling anecdote on myself. When I started, I was a very young physics student in the early 90s. In the other corner of the world, because I am from Argentina, to me it was mesmerizing to see the incredible things that were built in Japan with these neutrino detectors in the base of huge mountains with huge reservoirs of purest water. To me, it was very enlightening to see, and a very encouraging to see the kind of developments that were developed on the other side of the world. And in a way, closing myself, like many of the participants today in our presentation, the circle, I myself joined the young person that I was some years ago, and I rejoice again knowing the learnings that we can have from Professor Kajita. Thank you very much for joining today.
Thank you. Can I start? Okay.
Yes, you can, yes.
Well, thank you very much for the kind invitation to this very interesting event. And I'm sorry for my bad video, but please allow me.
It gives to the ambience, actually. We're in a virtual world. So.
Okay, then let me share my slides. Okay, today I want to talk about unlocking the universe secrets with neutrinos. Okay, well, actually, this is the outline of this talk. First, I want to discuss what are neutrinos. Then, I want to discuss the Kamiokande experiment. This is the experiment I joined when I was a graduate course student. Then I want to move on to the Super-Kamiokande and the discovery of neutrino oscillations. I also want to briefly discuss the discovery of solar neutrino oscillations. Then, before finishing, I want to discuss neutrinos and the big mystery in the universe, and I'll summarize this talk. Okay, what are neutrinos? Well, let me introduce the birth of neutrinos. In the early 20th century, physicists were puzzled with beta decays. Well, beta decays are shown here. A nucleus emits an electron, and then this nucleus is converted to another nucleus. And if this is the truth, then we should be able to observe an electron energy which is a fixed single value. However, the measured energy spectrum of beta rays or electrons were continuous rather than a unique value expected for two-body decays. Well, indeed, physicists were puzzled. What happened to beta decays? Then, on December 4th, 1930, Pauli wrote a letter to Dear Radioactive Ladies and Gentlemen. And in this letter, he proposed when a nucleus emits an electron converted to another nucleus, at the same time, a new particle is emitted. Indeed, if this is the truth, then one can easily explain the continuous energy spectrum of beta rays or electrons. So, this was the birth of neutrinos. Then, after this proposal, there have been many ideas and experiments. And now we understand neutrinos rather well. And here I want to summarize what are neutrinos. Neutrinos are fundamental particles like electrons and quarks. And neutrinos are something like electrons but without electric charge. In fact, this feature, something like electrons but without electric charge, has a significant consequence. Neutrinos can easily pass through even the Earth, but they can interact with matter very rarely. And neutrinos have three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And finally, I want to mention that neutrinos have been assumed to have no mass. Now, you may wonder how we can study neutrinos. Well, let me explain how we study neutrinos. Of course, we cannot see neutrinos themselves. But as I mentioned earlier, neutrinos very rarely interact with matter, with the nucleus. Then, in this interaction, typically a charged particle is emitted. Of course, we have various ways to observe these charged particles. For example, if the nucleus is a water nucleus, then this charged particle should propagate in the water. And when they propagate in the water, photons are emitted. Then, of course, we can observe these photons by photodetectors. And this way, we get information on the neutrino interactions. And therefore, this way, we study neutrinos. Now, I want to move on to our experiment, Kamiokande. Let me talk about the motivation of the Kamiokande experiment. In the 1970s, new theories of elementary particles predicted that protons should decay with the lifetime of about 10 to 30 years. Well, of course, 10 to 30 years is a very long lifetime, but people realized that indeed it is possible to observe this long lifetime. Therefore, several proton decay experiments began in the early 80s, and one of them was Kamiokande. And in the middle of this slide, I show the sketch of the Kamiokande experiment. It was a large water detector. It had about 16 meters in diameter and 60 meters high. and it contained 3,000 tons of very clean water. And if a proton inside this tank, namely protons in the water, if the protons decay, then 2 or 3 charged particles should be emitted. Then, in this case, these particles emit Cherenkov photons or simply photons. And therefore, if we have photodetectors, we can observe these photons. And therefore, this way, we would like to observe proton decays. Well, when I was an undergraduate course student, I was excited with this idea, and I thought that Kamiokande must be a very important experiment, and I joined Kamiokande. By the way, in the right side, I show the location of the Kamiokande experiment. It is in the mountain area in Japan. So the Kamiokande experiment was constructed under a mountain. And here in this slide, I want to show how we constructed the Kamiokande detector. Well, I said Kamiokande was a large water tank. It had 60-meter high. Therefore, it was not easy to install the photodetectors onto the detector wall. And after some discussions, we decided to use these plastic boards to install the photodetectors onto the inside of the tank or detector. Anyway, this installation work was very successful. And after several months of the installation work, we started the experiment. In fact, I enjoyed these works very much. And also, I was excited because I thought that the data from Kamiokande might contribute to understand the universe much. And around that time, I decided to become a physicist. Well, around that time means when I was the first year Ph.D. course student, I decided to become a physicist. Well, we wanted to observe proton decays. However, we have a serious background. That was the neutrinos. In fact, these neutrinos are produced in the atmosphere of the Earth. As you may know, there are cosmic ray particles. They are high-energy particles coming from the universe. And these cosmic ray particles, once enter into the atmosphere, they interact with the air nucleus, typically producing pions. But pions are unstable, and they decay to other particles. And therefore, and during this decay, neutrinos are created. And these neutrinos essentially simply pass through the Earth and fly to the universe. However, some of them interact in the Kamiokande detector, and they are the most serious background to the proton decay searches. Now, I want to briefly mention why we needed to worry about the atmospheric neutrinos. In 1986, we noticed that there might be much fewer atmospheric muon neutrinos observed in Kamiokande. We thought that we should have some problem in our data analysis. So we seriously studied what was wrong. And in fact, after about 1 year of studies, we concluded that the missing muon neutrinos cannot be due to any major problem in the data analysis. And we thought we should report our data to the physics community. So we wrote a paper. In fact, this paper was quite simple. We simply reported the number of muon neutrino events we observed. That was 85, and compared with the expectation, which was more than 140. Clearly, the number of muon neutrinos were much fewer than expected. In addition, we also counted the number of electron neutrino events observed and compared with the expectation. For electron neutrinos, the data agree with the expectation. That's all we reported. Well, although we had no clear idea what was the cause of the problem, I was most excited with the data. I thought that the data might be indicating something new. In fact, as a scientist, it was the most exciting time. And therefore, I decided to concentrate on this topic. Well, of course, we didn't know what happened. What was the cause of the missing atmospheric muon neutrinos? However, from the early days of this problem, we have been thinking that maybe the missing atmospheric muon neutrinos are due to neutrino oscillations. And here in this slide, I want to tell you what are neutrino oscillations. If neutrinos have mass, neutrinos change their type from one type to the other. For example, as shown in this figure, if a muon neutrino is created at the starting point and propagate to the right, then at some point, you find that the probability that muon neutrino to remain muon neutrino goes down. And these particles, if they propagate further, the probability that muon neutrino to remain muon neutrino come back to unity. Then probability goes down, go back to unity, goes down, and so on. And when the muon neutrino disappeared, tau neutrino should be appearing. So this is neutrino oscillations. And if this is happening, one can easily explain why the observed muon neutrino event was much fewer than expected. Well, that was a very interesting idea. However, there could be other possibilities. Therefore, we thought we need to find out if the muon neutrino, if the missing muon neutrino is due to neutrino oscillations or due to some other reasons. So we thought we need to have other measurement that could tell if the missing muon neutrino events are due to neutrino oscillations. And for this, we thought this way. As I mentioned, neutrinos are created in the upper atmosphere of the Earth, and these neutrinos come to the detector after traveling a short distance, maybe 10 to 20 kilometers. Then these neutrinos may not have enough time to oscillate. On the other hand, neutrinos are created in the other side of the Earth, and these neutrinos must propagate a long distance, typically 10,000 kilometers before arriving at the detector. Therefore, these neutrinos might have long time to oscillate. So, if we think this way, we thought we should observe an asymmetry of the up versus down-going flux of muon neutrinos. However, we realized that the Kamiokande 3,000-ton detector was too small to observe this effect, and we needed much larger detector, and therefore we needed Super-Kamiokande. Now I want to move on to the Super-Kamiokande and the discovery of neutrino oscillations. Well, here I want to discuss Super-Kamiokande. Super-Kamiokande is a 50,000-ton water Cherenkov detector. It has about 40 meters in diameter and 40 meters high. And in the right side of this slide, I show a photo of the Super-Kamiokande. And you may realize how big the detector is. By the way, I want to mention that Super-Kamiokande is an international collaboration. At present, we have about 230 collaborators from 11 countries. Now, I would like to briefly discuss the history of the Super-Kamiokande experiment. This photo shows the beginning of the Super-Kamiokande collaboration between Japan and the United States of America. This photo was taken at our institute, probably in 1992. At that meeting, we discussed how we collaborate in Super-Kamiokande. And indeed, our discussion was successful. We agreed to work together in Super-Kamiokande. And in fact, I want to mention, well, before Super-Kamiokande, we had Kamiokande in Japan. In addition, in the United States, there was another large water detector called IMB experiment. So this collaboration, we come together in the Super-Kamiokande collaboration, we come together with the expertise of the Kamiokande experiment and the IMB experiment. So we thought this collaboration should be successful. Indeed, we worked together from the beginning, and this photo shows the construction of the Super-Kamiokande detector. The photo was taken in the spring of 1995. So every day in 1995, these many people come into the detector, worked together to construct the Super-Kamiokande detector. And also, I want to mention, maybe about 70 to 80% of them are physicists. So we work together, physicists work together to construct the Super-Kamiokande detector. Well, and the experiment started in the spring of 1996. And in 2 years, we were able to report our first significant result. And here I show the copy of our presentation at the Neutrino Conference in 1998. In particular, could you see the lower panel? This is for muon neutrinos, and the horizontal axis is the neutrino arrival direction. 1 means downgoing neutrinos, and -1 means upward-going neutrinos. They came from the other side of the Earth. And the black circles with error bars show the data, and hatched histograms show the theoretical prediction. And in this prediction, we didn't include neutrino oscillations. Then you find for downgoing neutrinos, the data and the expectation agreed quite well. But for upward-going neutrinos, data showed a significant deficit, compared with the expectation. And the data can be very well explained if we assume neutrino oscillations, namely neutrinos created in the other side of the Earth propagate in the Earth, and while propagating in the Earth, the neutrino type changes from mu neutrino to tau neutrinos. Therefore, when these neutrinos come to the Super-Kamiokande detector, the probability that a muon neutrino remain as muon neutrino is just 1/2. So this way, we were able to convince the world neutrino community that neutrinos oscillate. Therefore, we were able to convince them that neutrinos have very small mass. Of course, we reported our result at a conference for neutrino physicists. However, I want to mention that this result was even mentioned by the US president. In fact, the US president at that time was Clinton, and he gave a talk at MIT's 1998 commencement. And in the middle of his talk, he mentioned about the discovery of neutrino oscillations. And he said, just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories, from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. Of course, as the US president, he mentioned that in Super-Kamiokande, US physicists were working together with the Japanese physicists. Then he mentioned the larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with the others, and our place in time. Well, I clearly remember that when we hear this talk, we really felt that we were really honored to hear this kind of remark from the US president. Now, I'd like to move on to the next topic, that is the discovery of solar neutrino oscillations. Now, first, I want to talk about solar neutrino problem. The sun generates energy by nuclear fusion processes, and neutrinos are created by these processes. Therefore, the observation of solar neutrinos is very important to understand the energy generation mechanism in the sun. Therefore, the pioneering Homestake experiment was designed and indeed observed solar neutrinos for the first time. However, there was a problem. The observed event rate was only about 1/3 of the prediction. This is the solar neutrino problem. And this problem was already known in the late 1960s. Well, during the 20th century, there were several other solar neutrino experiments, and all these experiments indeed observed smaller solar neutrino flux than expected. However, during the 20th century, it was not possible to understand why there were fewer solar neutrino events observed in these solar neutrino experiments. Then, finally, the snow detector was able to tell us why there was missing solar neutrinos. And the snow detector was located very deep underground, 2 kilometers from the surface, and it used 1,000 tons of heavy water, D2O. And in fact, by using heavy water, they were able to tell us why there were missing solar neutrinos. Indeed, by using heavy water, the snow experiment can tell us the total neutrino flux independent of the neutrino type. And if they observe the total neutrino flux, they found that the total neutrinos coming to the Earth is just expected. In addition, the snow experiment is able to observe the electron neutrino flux. And if snow experiment observed the electron neutrino flux, the observed event rate was about 1/3 of the expectation. Since the sun can generate only electron neutrinos, therefore the result indicated that somewhere between the center of the sun and the Earth, the electron neutrinos are converted to other neutrino types. So this way, people were convinced that the missing solar neutrinos were due to neutrino oscillations. Well, I talked about the discovery of atomic neutrino oscillations and discovery of the solar neutrino oscillations. And indeed, neutrino physicists were really excited. And since the discovery of neutrino oscillations, neutrino physicists have been studying neutrino oscillations in very, very details. And here I show the list of the neutrino oscillation experiments. I'm not going into details, but I just want to mention that there are so many neutrino oscillation experiments in the last 25 years or so. And I'd like to let you know that neutrino physicists were really excited with neutrino oscillations and therefore with the very small neutrino mass. Now, before moving on, I'd like to mention what I have been thinking. It took more than a decade before we concluded that the missing atomic neutrinos were due to neutrino oscillations. But we think that we were lucky because we got the conclusion rather quickly. As I mentioned, to understand the missing solar neutrino problem, it took more than 30 years So in our case, we only needed about 10 years. So I think we were lucky. Also, please keep in mind that there are many things, not just in research, but in many other jobs that take long time to reach conclusions. I think that finding new questions is almost as important as solving questions. And I hope that you remember the importance of the teamwork, which is typically very important to accomplish difficult things. And finally, I hope you do not forget the importance of pure science that expands the horizon of the knowledge. Now, in the remaining 10 minutes or so, I want to talk about neutrinos and the big mystery in the universe. Well, in the previous slides, I mentioned that we were really excited. Neutrino physicists were really excited with the neutrino oscillations. But you may wonder why we have been so excited. Well, electrons have mass, charged leptons have mass, quarks have mass. So all the other particles have mass. And therefore, in a sense, it is natural that neutrinos have mass. You may wonder why neutrino physicists were so excited. Indeed, we have been excited, and I'd like to let you know why. Now, during the last 25 years or so, neutrino physicists have been working hard to understand the neutrino mass. And now we understand neutrino mass rather well. And therefore, I would like to show the neutrino mass here in this plot. Oh, by the way, I forgot to mention, the horizontal axis is the mass. Okay, now let me show the neutrino mass. They are here. So you find that neutrino mass are plotted in a rather different place in this plot. And please be careful about the horizontal axis. Here, the 1 unit is 100. And therefore, if the separation is by 2 units, that is 10,000. So you can easily find that the neutrino mass is approximately, or maybe more than, 10 billion times smaller than the corresponding mass of quarks and charged leptons. 10 billion times smaller than the other particles' mass. Very small. And therefore, we believe this is the key to better understand elementary particles and the universe. Of course, if we know why neutrino mass are so small, then, of course, we understand elementary particles better. But at the same time, we think that the small neutrino mass is a key to better understand the universe. Why? Well, let me explain. Well, here I show a photo taken by the Subaru telescope in Hawaii. You see many galaxies. And these galaxies, well, we know that these galaxies are all made of matter. Well, you may think this is trivial. However, in fact, physicists are not understanding why the present universe is dominated by matter particles. Let me tell you why we do not understand the present matter-dominated universe. Well, 13.8 billion years ago, the universe began with the Big Bang. And the Big Bang universe was extremely hot. And in the extremely hot universe, always matter particles and the antimatter particles were created simultaneously. That means in the Big Bang universe, the number of matter particles and antimatter particles should have been equal. Then, with the universe expanding and cooling down, these matter particles and antimatter particles begin to meet and annihilate. And if this matter and antimatter annihilation continues, then we naively expect there should be no matter particles, no antimatter particles at the present-day universe. However, as we know, at present, essentially we have only matter particles in the present-day universe. So we do not understand why the present-day universe is dominated by matter particles. And indeed, we do not know why. But there's an interesting idea. Well, according to this idea, neutrinos with very small mass might be the key to understand the big mystery of the matter in the universe. Well, since this is just a theoretical idea, we have to test this idea experimentally. And indeed, now there are very large neutrino projects going on, one in United States, one in Japan. And in this, and in these neutrino experiments, we'd like to know if neutrinos are related to the origin of the matter in the universe. And we'd like to observe if neutrino oscillations of neutrinos and those of antineutrinos are different. And indeed, if we observe the difference, that would be the first evidence that neutrinos are relevant to the matter in the universe. However, we know that the present generation of neutrino experiments are not powerful enough. Therefore, we need the next generation neutrino experiments, and these are these two projects going on in United States and in Japan. Now, I'd like to talk about the new neutrino projects that is going on in Japan. The new project is called Hyper-Kamiokande. It is going to be an extremely large water detector. It will be about 70 meters in diameter and 70 meters high. And we hope that this experiment may unlock the secrets of the universe. And neutrino physicists were excited with this project. And at this moment, Hyper-Kamiokande collaboration has about 600 collaborators from 22 countries. At present, the experiment is still on construction stage. In fact, still the excavation of the very large underground cavity is going on. But physicists were expecting to start the experiment in 2027. So we are really excited with this new generation of neutrino experiments. Okay, let me summarize. Neutrino oscillations were discovered by large underground detectors. The discovery of neutrino oscillations opened a window to study physics beyond the present standard model of particle physics. And neutrinos with small mass might also be the key to understand the fundamental question of the universe. And finally, I want to mention that there are many unanswered questions in the universe. And I hope that scientists will answer these questions and find new and big questions. Okay, that's all from me. Thank you very much.
Thank you very much, Professor Kajita. It was a fantastic presentation, and it was a very comprehensive description of what has been happening over this past almost century of advances in this very interesting field of physics. Thank you very much. It was very, very enlightening. One thing that I would like to mention to the people is clapping virtually inside of the aula. Thank you very much for the participants. The thing that I would like to say to all the participants that are online in the virtual world is, if you have any further question, we have a few already, but if you have any further question to Professor Kajita, please write them down in the chat, and I will be happy to translate to repeat it to him. Okay. This is now the Q&A session. We can start. I do not know if the questions will show in the bottom. If not, I can start saying the first one that I have in my list, which is the following, and actually picks up, is very timely. It was one of the questions by the audience, because it's exactly the way in which you finished your presentation, which is, and I think that which is the following. 20th century has been a phenomenal era for physics discoveries. And I would add, because of the unprecedented rate at which all our conception of the world completely changed in the late 19th and all 20th century. According to you, which are the main open questions for physics as a discipline, and which are the challenges that you find in order to be able to answer them?
Okay, thank you. In fact, well, in the universe, there are many unanswered questions. In particular, well, we knew that there exist dark matter particles. In fact, we knew dark matter exists for essentially for the last 90 years, but we do not know what are they. And well, this is a very important question that we should answer. In addition, recently, at the end of the 20th century, people realized that in addition to the normal matter and dark matter, there are another significant contribution to the universe, that is dark energy. We have no idea what are they. Mm-hmm. This is a very important question, and well, certainly we hope that future generation of scientists will tell us what are dark energy.
Mm-hmm. Correct. If I may add, I think that the difficulty is that over and over, the time the resources that need to be invested as well to new discoveries also become more and more large scale, because also the sizes of the energy we're speaking about as well is something that is completely changing in scales over and over, because this is what actually opens the question. Thank you very much. The second question that I have in the list is, it will be shown in a second, is what kind of advice would you give to scholars from around all the disciplines, I think not only limited to physics, for long-term success in science?
Okay, thank you. Well, as I mentioned, for scientists, it's very important to find new questions, new and fundamental questions. So I hope future generation of the scientists try to find out new questions. Well, it may take long time to answer these questions, but I believe finding new questions is a very important part of the scientist work.
Okay, thank you very much. I have another question that is the following. Over your presentation, it has been clear that exactly because of neutrino oscillations, in general, the number of neutrinos that you end up detecting on the experimental setup is much lower than what the models back in the day were predicting. This actually most likely made much more challenging to detect the very first ones too. Okay, and the question that I have is, what was the discussion in the physics community back in the day? Was it that the experimental setups were be blamed because of this lack of detection? Is it because people were saying that perhaps the theory was wrong? What was the discussion, and which were the more plausible explanations?
Okay, thank you. Well, let me talk about the story about the solar neutrino problem. Well, as I mentioned, the first solar neutrino observation was carried out in the late 1960s. And after that, people realized that there are missing solar neutrino problem. And in fact, people had no idea what was going on. Therefore, some people doubted that there might be some problem in experimental details. Or some people thought that there might be some missing element in the theory side, solar neutrino flux prediction. Or some people thought maybe this is due to neutrino oscillations. Yeah, but anyway, during the 20th century, this kind of discussion going on.
Fantastic, good. Thank you very much. There are two more questions. I think that we can go to the next one, please. I am waiting for it to materialize in the chat. The question by another person from the audience is whether, because you were mentioning different kinds of neutrinos, each neutrino is associated with a different kind of lepton, whether the three kinds of neutrinos, electron, muon, and so on, have the same mass or not.
Okay, thank you very much for this question. Well, the answer is no. They have different mass. And in fact, it is fundamentally important that three neutrino mass are different. If the mass is the same, then we do not expect neutrino oscillations. So the experimenter clearly tells us that the three neutrino mass are different.
Okay, thank you very much. There is another question. Now I can go with the follow-up of the previous one because it's very related. Is how to know the transfer probability of these three kinds of neutrinos. We are getting technical.
Oh, this is maybe too technical.
Okay, good.
Yeah.
we,
Anyway, well, related to the previous question, well, depending on the neutrino mass difference, the frequency of neutrino change their type changes. If the neutrino mass difference is small, then a neutrino need a long distance to change their type.
Okay. Okay, good. Thank you. And the final question that I have, at least from my list, is the following. How is it that the dimensions for the Kamiokande, Super-Kamiokande, now Hyper-Kamiokande, were calculated? Is it there a theory? How is it that the dimensions were decided for the different Kamiokandes iterations? Are there theory specific parameters that led to these sizes?
Thank you. Thank you for this question. Well, of course, we have reasons. Well, Kamiokande, the size of the Kamiokande was determined to observe proton decays, assuming that proton lifetime is about 10 to 30 years. Now, the size of the Super Kamiokande was decided, but one of the main scientific topic was the solar neutrino observation in Super Kamiokande. And we thought we need to have more than 10 solar neutrino events per day in order to do a detailed study of solar neutrinos. And from this constraint, we decide the size of the Super Kamiokande detector. Then finally, Hyper-Kamiokande. In Hyper-Kamiokande, we would like to know if the oscillation of neutrinos and those of antineutrinos are different. And actually, in order to do this experiment, we use accelerators to produce neutrinos. And therefore, we can estimate how many neutrinos are produced in the accelerator and how many neutrinos come to the Hyper-Kamiokande detector. And therefore, from these numbers, we can simply calculate the size of the Hyper-Kamiokande detector. So in all three generations of the detectors, we have reasons reasons for these detectors, for the size of these detectors.
Fantastic. Yeah, and actually, the picture that you showed on the size that Hyper-Kamiokande has now compared with the mountain size shows also how little neutrinos interact with regular matter. So indeed, that is incredible places. Fantastic. Professor Kajita, I am really thankful for your presentation today, for the time that you devoted to us, and I'm also really thankful to the audience that were engaged in the questions and participated in this virtual environment. Thank you very much for those that joined online, and thank you very much for your time. It was a very enlightening presentation, and we learned a lot today. We really appreciate your participation opening today. And Yanis, if you want to say a few words.
Yes, again, thank you very much, Claudio, for your wonderful moderation. And thank you so much, Professor Kajita, for this wonderful talk today and giving us the insights into the secrets of the universe. As Claudio said, we really learned a lot today. And thank you so much for participating in this really new format of getting together and immersing into science communication. So thank you again, Professor.
Thank you very much.
Thank you very much, and to all the online participants, thank you very much for joining. I hope to see you again in another one of the events that we are planning in the Swiss Pavilion in the Metaverse. Thank you very much. Have a good evening there in Japan, Professor. Have a nice
Thank
time.
you. Bye-bye.
Goodbye.